We're going to work on an ALEKS problem that deals with calculating the pH of a weak acid solution. In this example, the acid dissociation constant of acetic acid is 1.8 times 10 to the negative fifth. They want us to calculate the pH of a 3.3 molar solution of acetic acid and to be sure to round our answers to 1 decimal place. Since we're dealing with pH and final concentrations of H3O+, we're going to have to set up an ice table. So our weak acid, when we dissolve it in water, would dissociate to H3O+ and acetate. They also gave us the Ka value, so I'm going to go ahead and write that down. Once I make sure that my equation is balanced, I can go ahead and set up my ice table. Initially, they give us 3.3 molar of our acid. We can ignore water because water is not included in our Ka expression. Initially, we have 0 concentration of H3O+ and 0 concentration of the acetate. For our change, it's plus or minus the coefficient times x. So on the reactant side, we're going to say minus x. For the product side, we're going to say plus x for both of those. Equilibrium is initial plus change, so 3.3 minus x. 0 plus x is just x. And I'm going to set up my Ka expression, which is equal to the concentration of H3O+ times the concentration of the acetate over the concentration of the acid. Before I continue, I want to try and make the math as easy as possible. So I'm going to go ahead and assume that x is so small that it really won't make a big difference to the final equilibrium concentration. Of course, I'm going to have to go back and check that before I give a final answer, but let's go ahead and try to assume that first, and if it doesn't work out, we can go ahead and work it out the long way. So let's go ahead and plug in our numbers that we do know. Our Ka value was given. Our equilibrium concentration is x. Our acetate equilibrium concentration is x. And equilibrium for acid is just 3.3 because we're going to assume that x really is so small, doesn't make a big difference. Let's go ahead and clean this up. So we're going to get 5.94 times 10 to the negative 5 equals x squared. We're going to take the square root of both sides. We're going to get 7.71 times 10 to the negative 3 molar. Before I continue, I need to make sure that we assumed correctly. So that's really called check the 5% rule, which says that I am assuming that this x is either 5% or less than the original initial concentration. So I'm going to plug that in. And this equals to 0.23%, which is good. That means it's less than 5%. So now my assumption was right. I can continue with the story problem. Remember that pH is equal to the negative log of the concentration of H3O+. And our concentration of H3O+ is just 7.71 times 10 to the negative 3. Final answer has to be to 1 decimal place, so pH equals 2.1. Let's try another example. In this example, the acid dissociation constant of hypobromous acid is 2.3 times 10 to the negative 9. They want us to calculate the pH of a 2.1 molar solution and round our final answer to 1 decimal place. So let's go ahead and set up an ice table. So when we dissolve our weak acid in water, it would dissociate to H3O plus and hypobromides. And they gave us the Ka value. Once I make sure my equation is balanced, I go ahead and set up an ice table. Initially, we have 2.1 molar of our acid, 0 of our H3O plus, and 0 of our BRO minus. For our change, we have minus X on the reactant side, plus X on the product side. Equilibrium, we're just going to be adding initial plus change. I want to set up my Ka expression, which is the concentration of H3O plus times the concentration of BRO minus over the concentration of HBRO. Before I continue, and I want to make my math a little bit easier, I'm going to go ahead and assume that X is so small that it does not make a big difference in the equilibrium concentration of HBRO. I'm going to have to come back and check that, but let me go ahead and plug that in, making that assumption. So I'm going to just go ahead and plug in the numbers. I'm going to go ahead and clean this up. I'm going to take the square root on both sides. Before I continue, I'm going to go ahead and check and make sure that that X is 5% or less than the equilibrium concentration. So let's go ahead and check that. And this is a really small number. So it's less than 5%. So I can go ahead and make that assumption. Let's go ahead and type this into our pH formula. pH equals negative log of the concentration of H3O plus. pH equals negative log, we solved for our X, which is our H3O plus concentration. Final answer needs to have one decimal place, so pH equals 4.2. Good luck and keep practicing.